Good day, class, and welcome to physics class, physics lesson. We are going to continue from where we stopped last time in propagation of wave motion. Last time we defined wave, and we also explained some types, examples, and the classification of wave, and also show how to represent wave in longitudinal and transverse waves. Today we are going to continue from where we stopped, and we are going to touch other things on wave, such as general representation of wave. We're also going to define terms using wave equations, and also we are going to go into wave equation properly and do calculation after that. So to continue, we have to define some general representation of wave. Yes, last time we explained wave into two major ways, which are transverse and longitudinal wave, because of the ways through which particles of medium move in relation with the traveling wave. We are able to explain what is transverse wave and longitudinal wave. So today we are going to generally represent wave, anything that has to do with wave, how it can be represented in a function or in an equation. So that is exactly what we are going to do today. So all waves, when in progress, when moving, is plotted in graph, where y-axis represents the direction of vibration of particles, while x-axis represents the direction of propagation of waves. And that helps us to get a graph that looks like this. So this is generally a graph that represents wave motion. This graph is called sinusoidal graph, or in simple form, sine function graph or cosine function graph. Yes, that is how, if you have known the mathematics of sine and cosine, this is the graph that represents sine and cosine function. And also that is exactly the nature in which wave adopts. You can see that in the motion of wave, it's a sort of doing a kind of to and fro motion, in which half of its oscillation is spent upwards and half is spent downwards, or positive and negative directions. So that is why we have a graph function that looks like this. And from here you can see some terms we are going to define. This represents the y direction, while this represents the x direction. Along the y direction we have amplitude, that is the maximum displacement of wave from the equilibrium position, and we have along the y-axis we have the wavelength, which shows the distance moved by a wave from one point to another related point along the wave, from crest to crest or from trough to trough. So there are other things we are going to see as we progress in wave in this. So the next thing we are to talk about is the terms used for describing wave motion. One of that is the amplitude I've just explained to you. This is defined as the maximum displacement of particle in a wave from its equilibrium position. It is measured in meters, and this graph truly represents what we mean by amplitude. amplitude is measured from equilibrium position along the y-axis to the maximum displacement. So that distance in vertical direction gives us what amplitude is all about, and is in meters, meaning that is same as distance. So the next we are going to talk about is the period. The period, this is the time required by the progressive wave to perform one complete cycle or oscillation. It is measured in seconds, and this represents what we mean by wave period. Wave period, as we can see, is determined from one point to another. The time taken to complete one period from one point to another, from crest to crest, or from trough to trough. That shows one complete cycle has been completed, and is a time function. Is a time function. So that is what period is measured in seconds. That is to show that is a time function. So the next one is frequency. Frequency of wave. This is the number of complete wave passing a point in 1 second. It is measured in hertz. It is measured in hertz, and you can see two different frequency: high frequency and low frequency. When we mean high frequency, this is how it looks. That is how the wave function is described. And when we talk about low frequency, that's how the wave function is described. Moving forward, we have what we call the wavelength. This is the distance between the identical points on a wave. That is one full wave. It is measured in meters, and this describes exactly what we mean from crest to crest, the distance from crest to crest, or from trough to trough, from one point to its identical point along the wave. Describes what wavelength is all about. It is measured in meters. That is to say that is a distance. Is distance, and it is distance measured along the x-axis. It is measured along the x-axis, unlike the amplitude that is measured along the y-axis. So this one is measured along the x-axis. It shows its distance describe one full wave, one complete wave. So that is what wavelength is all about. Next, we have what we call the wave speed. This is the distance waves cover in 1 second. It is measured in meters per second, just like how we have the normal speed or velocity. That is what wave speed is stand for, or wave velocity stands for. It is same as, wave speed is equal to frequency times wavelength. What we have as wave f lambda. F stands for frequency and lambda stands for wavelength, as can be described in the triangle we have represented. So that is what wave speed is explained as in wave. The next, we talk about the wave equation, and wave equation is described as the distance moved by wave over the corresponding time taken, and it is given as v equal to x over t. S stands for distance moved by wave, and t stands for time taken. Next, we have what the wave speed again can be explained, as I told you before, wavelength times frequency. Wavelength times frequency, lambda f, or f lambda, represents wave speed. The next is time. Time is equal to, that is, period is equal to time covered over number of cycle. Time per cycle. Time per cycle is short explanation of what period stands for, and the frequency on its own is cycle per time. So you can see that frequency and period are inversely proportional to each other, as we can be described in this equation. T is equal to 1 over F. T, capital T, stands for period, while F stands for frequency. So that's the relationship between period and frequency. So that is what that stands for. And next we are going to talk about the proper wave equation of traveling wave. The equation of traveling wave can be written like a sine or cosine function, just as we have here, sine or cosine function, y equal to sine theta or y equal to cos theta. And that is given rise from what? From this graph. I told you initially that this graph describes a sinusoidal graph or y function graph or s function graph. So that is how wave equation is normally described. We use sine function or cosine function to represent wave equation. So whenever we have a graph like this, we call it wave graph, or we call it sinusoidal graph, or we call it sine or cosine graph. So they are all the same thing. So when a wave moves in this way, it can be written as y equal to sine theta or y equal to cos theta, because both of them have the same graphical representation. So moving ahead, we have angular frequency is equal to theta over time. Yes, we have theta here to represent the angle an object makes. Take for instance, when an object is moving in a circular path, this angle, it starts from 0 and increase from 0 to 90, from 90 to 180, from 180 to 270, from 270 to 360 before it completes a cycle. When the angle of 360 represents one cycle. So that is just what we mean when we say one oscillation or one cycle. It represents angle 360, and that is why we have this theta here. This theta for one complete cycle represents 360, and in radians we have theta 360 to be 2 pi. So that's why we normally have this kind of representation, that angular frequency is what? 2 pi, 2 pi. This 2 pi means angle, as we can have here. Just consider this is describing, these two equations are describing the same thing. This is normally in degree, while this is in radians. So when it is given in radians, angle divided by time taken, and this one is given angle in radians, that is 2 pi, meaning 360, one complete cycle over one complete period. A period is normally made in one complete cycle. So that is why when you have one complete angle cycle over one time cycle, you have it as angular frequency. So that is what angular frequency stands for. In most of our graphs, as we proceed, we are going to see, are going to have this angular frequency in representation of wave graph or wave function. So that is coming from this. When you cross multiply, for example, this, you see that theta is equal to WT. So we are going to be substituting wherever we see theta in this in wave graph or wave function, we substitute it with WT, or that is the product of angular frequency and time taken. So that is where this comes from. So this also represents exactly what we are talking about, which is part of wave graph, as we are going to see as we proceed. When it is given in calculation, we are going to be using this. This is simply given in this way. If I should elaborate further, this is simply y is equal to A stand for amplitude sine WT minus KS. So this W, as we have here, is same as 2 pi over T, or 2 pi F. That is angular frequency is equal to 2 pi F, which is equal to 2 pi over T. So that is what we have used to represent this. So taking the form A sine WT, which is A sine 2 theta over capital T multiplied by T. So this and using WT are the same thing, just that angular frequency is same as 2 pi over T. And also K, as a typographical error here is X, there must be S there. So this 2 pi over lambda stands for wave number. That is wave number K is given as 2 pi over lambda. So there must be an X representation in that to make that formula to be complete. There's a typographical error in this, so there must be S there. So this describes what we call wave number, which we are going to be using to determine the wavelength of a wave. So going further, this can be factored out. 2 pi can be factored out from this, and we can have the equation in this way: y equal to A sine 2 pi into bracket T over capital T plus or minus X over lambda. So this graph, or this function and this function, are just the same thing. It's just that from here we extracted 2 pi, which is what we have here, to make this change from this to this. So they are one and the same thing. This graph will be used that's what we call equation of traveling wave, which we are going to be using to solve problems in equation of traveling wave or progressive wave. So this is very, very important, how to make a good study understanding of this. Next, we talk about the same graph can also be written in this way, or the same function can be written as y equal to A sine 2 pi over lambda Vt plus X. This is still the same as the same graph. Here we just substituted the value of pi, v, which is wave speed, and when that alteration is made, you see that try to insert v in this. You know that we have said before that v is same as f lambda. So when we do that, this equation will change, or that equation will change from there to this. So they are the same thing. Also, there is a plus or minus in this. This shows the direction in which the wave is moving. It can be moving from left hand side to the right hand side. In that case, it's a positive movement. Plus is supposed to be there. Or some wave can be moving from right hand side to the left hand side, which is negative movement. In that case, we have a negative representation. So that is what brings about the plus or minus representation in between this and that. So that is it. So next we talk about the calculation. Let's express ourselves by using this calculation to explain what we mean by equation of progressive wave. So the equation says the displacement of a plane progressive wave is given by y equal to 12.5 sine 24 pi t minus 0.5 pi x. where the symbols have their usual meaning. Y and S are in meters and T is in seconds. For the wave, determine I the frequency, I the wavelength, and I the wave speed. So to handle this is the solution we are going to take. We are given that Y is equal to 12.5 sine 240 pi t minus 0.50 pi x. So in this, we have to equate this with a related general wave graph function, which is y equal to a sine wt minus ks. So that is the general wave graph. So we have to find whatever thing we need. We have to do comparison. So had it been we are asked to find the amplitude, you can see it that's from this that amplitude A is same as 12.5 by comparison 12.5 meters. So that is what is the amplitude. Again, we are asked to find the frequency. To find the frequency, we use this. We know that angular frequency is equal to 2 pi f. So we are going to find it from here by comparing this and this. So from there we have that 240 pi is equal to angular frequency. So angular frequency, which is 2 pi f, is equal to 240 pi. So pi, we cancel pi, and 2 we cancel itself and cancel this to give us 120. So the frequency is equal to 120 hertz. Hertz is actually per meter. That's what it stands for. Moving ahead to find the next, we are told to find the wavelength. To find the wavelength, we are going to use wave number. K is equal to 2 pi over wavelength. So wave number, as I have represented here, K stands for this. K is equal to 0.5 pi. So K, which is equal to 0.5 pi, is equal to 2 pi over lambda. So that pi cancels pi, and we have wavelength to be equal to 2 over 0.5, which will give us 2 divided by 1 over 2, which will be equal to wavelength is equal to 2 times 1 times 2 times 2 over 1, which is equal to 4 meters is the wavelength. So the next we are asked to find is the wave speed, which is V. It's represented by V f lambda. So that will be equal to, substituting the values we have already found for f and for wavelength. F is 120 times 4, and that will give us, using our calculator, 120 multiplied by 4 is equal to 480 meters per second. So that is the calculation. So with this, you can always solve a problem of a wave equation. That's exactly how wave equation can be solved. Thank you very much.